So I hope you're getting the idea of kets being column vectors, bras being row vectors, and we take the inner product, which we used to call the overlap integral and we'll still call the overlap integral because it's equivalent, and that basically functions are vectors in a very high dimensional space. I'm going to introduce something now which I've avoided including early on just to try to minimize confusion with the Dirac delta function. There is another delta, and you've come across this now in other modules, which is called the Kronecker delta. The Kronecker delta we define like that, or we write like that, and it's equal to 1 if m is equal to n, and it's equal to 0 if m is not equal to n. So it's a very straightforward, compact way of representing the orthogonality condition. Don't confuse it with the Dirac delta. Okay, it's always clear from the context, and including the little subscripts here, when we're using the Kronecker delta and when we're using the Dirac delta. So that means we can write our inner product for, say, two eigenkets, let's say un, really straightforwardly. So this inner product, because we've got a basis set where our basis vectors are orthogonal, that means that unless m is equal to n, this is going to be 0. Only in the situation where m is equal to n is this going to be equal to 1. So it's a nice compact way of representing our orthonormality condition. The other thing I've been a bit, I don't know, breezy about, I guess, is the idea of a complete basis set. So completeness means that we can represent any function in terms of a linear combination of our basis states. So if we do have a complete basis set, there's a nice little identity that falls out of this, which is that this must be true. I'll state it and then I'll prove it. With that, I've written it specifically like that. That's the identity matrix. That's the matrix you're familiar with from other matrix problems. So zeros everywhere, apart from along the main diagonal. So there are a couple of interesting things about this. First of all, notice that we don't have a bra ket. We have a ket bra. Remember, always think in terms of matrix manipulation. So if we have a bra ket, we have a row by a column, and we've seen that gives us a scalar. We get the dot product, the inner product. However, it's the other way around, and that gives us a matrix. Not a scalar, a matrix. Hence, and in this particular case, it gives us the identity matrix, which means that this thing is an operator. What it does is it takes a ket, operates on it, and returns another ket. In this case, you just get back your initial state. So it's, in some senses, you might think not a very helpful operator. It turns out to be, for a number of different manipulations we'll do soon, a very helpful operator. But the important thing is here is an operator is a matrix. And we will see the Hamiltonian. We're going to see it both on the board. We're going to see it in a worked example. And we're also going to see it in terms of Python, in terms of how we can take the Hamiltonian for a quantum system and cast it in the context, or cast it as a matrix. So it's an operator. It's a Hamiltonian operator. It's a very important operator. How do we cast that as a matrix? We're going to see that. But for now, I'm not going to let this go without comment, because you can either accept that at face value, or we can think about how we might prove that. So starting with, okay, I've just rewritten this in terms of an index m. The reason I'm using m rather than n will become clear in a second. But again, don't get confused. I can call this whatever I like. It's just an index. So what we'd said was that this holds true. Which means that if that's the identity matrix, that when we operate on this with this, we should get this back. So we'll take that, set as an operator, and we're going to operate on this. So what do we get? Well, first of all, that is just that. So let's put that in. And now you might see why I chose a different index. So all I've done there, okay, let's put brackets around it, is insert that into the expression for the ket psi. Okay, let's move it up the board. Okay, so what we can do is we can loop around both our n and our m loops or indices, and what we'll have is Cm, which is just a scalar, remember that's just a number, by that ket, and then what we're going to have here is un, and it's going to become a bracket, but wonderfully we've got an orthogonal basis set, which just gives us that wonderful Kronecker delta I've just mentioned. So that's only 1 if m is equal to n, and I keep getting asked this question. All I'm going to do now is set n is equal to m, right? So, or m equal to n, either way around, it doesn't matter, it's just the index is the same. So that means we have which is what we defined. We were saying this was our state vector. We've operated on our state vector with our identity, and we've got this back, which is what we said was our state vector in the first place in terms of a linear combination of kets. And just work through that. It's a little bit subtle, I guess, in terms of the mathematics, but hopefully not too much. And basically we've shown that when we operate with that identity matrix, we return back our original ket, which is why it's called an identity matrix. But perhaps that's one important aspect, but the other important aspect, of course, is that instead of having a bra ket, we have a ket bra, and that's an operator. That's a matrix rather than a scalar. So we're going to take that idea, extend it further, and we're going to think about the Hamiltonian as a matrix now. So if an operator is a matrix, our key question is, well, what are the matrix elements? What are the numbers in that matrix that I need to actually carry out a particular operation, to operate on a given ket, to do quantum mechanics? Turns out that the matrix elements we need, pretty straightforward formula, but again, the logic in terms of getting the formula for those matrix elements is a little bit subtle and involves the identity matrix again, and a bit of mathematical trickery, but an elegant piece of mathematical trickery that's only going to take us a few lines. And that gives us the matrix elements. And once we have those matrix elements for a particular operator, then we're laughing. Then we can start doing some quantum mechanics, as I say. We have an operator. And we're going to do a trick. It really is a trick. We're going to take our identity matrix, or identity operator. It's a matrix, therefore it's an operator. And we're going to do that. These are just one, right? So this is unity, and we're just getting the same thing. So that is equal to that. But this really helps us in terms of defining what our matrix elements are going to be. And again, we're going to do the same trick in terms of using different labels for the elements, but just don't let that confuse you. I know it's confusing a lot of you, and I'll do my best to try and explain this as I'm going along, but we're just basically using different labels. So our identity operator, as we saw last time, let's write this one as n, is this, where again we're using u. These are our basis kets forming an orthonormal complete set. Right, there's our operator. And then on the other side we have the identity matrix again, but what we're going to do is we're going to label it now by m. Again, we can just use whatever we like. Let me move that across. Do it in terms of m. And we have this. So, better TypeScript, we go from there. That means we get this. Compare and contrast this and this. Make sure you can see where this comes from. But what we're ultimately doing this for, and why we did that little trick, in terms of the identity matrix, is to pull out this, which is all important, the matrix elements for this operator. The operator is a matrix, but we need to know the numbers in the matrix. And again, if you compare this to this, what you'll see that's what we have. Again, just as you're used to sandwiching an operator like this in terms of an overlap integral, remember this inner product is effectively your overlap integral. So what we've got here is an inner product where we've sandwiched the operator in, and the operator is operating on our ket. And then we've taken a bracket of this entire thing. We're going to see how that works in practice, both in terms of analytical pen and paper or chalk and blackboard mathematics, and also on a computer. And I know some of you hate coding. I'm sorry, I love coding. But for me, coding was essential in getting my head around quantum mechanics, getting my head around matrix mechanics. Actually, all of quantum mechanics has got to be said. So I hope it's helping some of you. And I know I've had quite a number of emails. Thank you. It's really kind of you saying that the coding is helping you and helping you get your heads around it. You hate it sometimes, but you appreciate that going through the pain is helping you get a better grip on the quantum mechanics. So we use this equation to fill in the values in our matrix, in our operator matrix. So we'll have 0, 1, 1, 0, 1, 2, 0, 1, 3, da 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 da, 0, 2, 1, 0, 2, 2, 0, 2, 3, da 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 da, da 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 da, da 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 da. Only issue is it's infinitely dimensional. Obviously, we don't do infinitely dimensional on a computer. We have to have a cutoff at some, hopefully quite high value of n, in terms of the number of matrix elements we're going to compute. But it's always a trade-off between accuracy. The higher we make that matrix, the larger we make that matrix, better an approximation we're going to get. But that approximation can be really good even with relatively few matrix elements. But of course it slows us down, particularly because this ultimately, we're going to have to perform integrals to work out what those matrix elements are. We'll see that when we get to some Python coding. So we've got that. The other thing that's really important to note is our operators, when we talked about them in terms of wave mechanics, said they were Hermitian, therefore they had real eigenvalues. These matrices have also got to be Hermitian. And what does that mean in the context of matrix mechanics? Well, we've already seen it, because the bra is the Hermitian conjugate, or the adjoint of the ket. It's exactly the same here. What we have is that for real eigenvalues, our operator matrix is equal to its Hermitian conjugate, or its adjoint, which we denote by a little dagger, which means that what we have is, let me do it like this, let me move this up the board. What we do is we take the complex conjugate and then flip rows and columns. It's the transpose, it's the complex conjugate transpose, or the transpose of the complex conjugate, whichever way you want to think about it. So first of all, we take complex conjugates of all of our values. And then what we do is we transpose that. As if by magic, that's what we end up with. Important thing to notice here is that our diagonal elements for an Hermitian matrix, the complex conjugate of our diagonal elements is equal to the diagonal elements themselves, which must mean that the diagonal elements are real. So, Hermitian matrix, diagonal elements are real, and to get from our original matrix to our Hermitian matrix, complex conjugate all the elements, then transpose rows, columns. Simple as that. It's all just spreadsheets. I'm simplifying it a little bit, perhaps oversimplifying it a little bit there, but honestly, this is what we're doing. Rows, columns, matrices, arrays, spreadsheets. Right. Hamiltonian matrix. So, we can write down, you know, we've seen this before, ad nauseum, yes. And we've seen it expressed like this. Well, these are our eigenkets of the Hamiltonian. So more generally, we can write that as some operator operating on our eigenkets gives us back some eigenvalue operating on our eigenket. Now you've seen, I'm not going through the details of eigenvalue problems. You've seen this in other modules. You saw it actually last year in general maths as well. You've looked at eigenvalue problems in a number of different other modules. I am not going to talk you through exactly how to do this. Now there are additional notes. You can look through those notes and see how this works in the context of matrix mechanics, but it's no different. It's an eigenvalue problem based around matrices. But it's nothing different in that we want to solve that. Nothing different to what you've seen before. I'm going to drop the little hat just to just hammer home, I hope, that this is a matrix. Oh, that's a secular equation. You've seen this before. Look, there's our identity operator again. So basically what we want to do is have a determinant of our matrix O, and along the diagonal, what we're going to do, because this is only one along the diagonal, O11, O12, O13, da 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 da, O21, O22 minus O23, da 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 da, O31, O32, O33 minus lambda, etc., etc., etc. And we want to set that determinant equal to 0 and solve to get our eigenvalues. To get our eigenvalues, we can work backwards to plug those back into the eigenvalue equation and work out what our eigenvectors are. Let's do that for a simple matrix now. Let's do a worked example on that. You'll see, but I'll stress again, this is nothing new. You've done this before. And one of the reasons you do quite a bit of matrices last year is to get you prepared in terms of this type of eigenvalue problem. And as you know, if you attended the drop-in sessions recently, the eigenvalue problem crops up across very, very many areas of physics. Okay, so this is the worked example in section 6.4.5 of the notes. There we go. Consider the matrix A, which is that. Is A Hermitian? Well, first of all, there are no imaginary components in there, so the complex conjugate is just going to be the same as that array. Then if we flip the rows and columns, we end up back with A, so indeed A is Hermitian, which is good because that means it's going to return real eigenvalues, which is very useful in quantum mechanics. Then B, find the eigenvalues and normalized eigenvectors of A. Are there any degenerate eigenvalues? So degeneracy means that two eigenvectors have the same eigenvalue. That turns out to be an important aspect of quantum mechanics, particularly when you get beyond one dimension and we go into two-dimensional systems and beyond. That degeneracy is important, so you'll see more about degeneracy next semester. So, to solve that, well, it's pretty straightforward in this case. We just subtract lambda off the main diagonal. 1 minus lambda, 1, 0, 1 minus lambda. And that's got to be equal to 0. You've done problems like this before. You've done eigenvalues before. I am not talking you step by step through this. If you don't see where these values come from, here are our eigenvalues. Zero, root 2, minus root 2. If you don't see where those come from, go back to your first year notes, general maths, go back to the drop-in sessions, the material there, go back and make sure that you can show that these are the eigenvalues. What we're doing, as it says there, is we're getting the determinant of this matrix set equal to 0, solving for lambda to get these values. Make sure you can do it. Then what we do to get our eigenvectors, and I'll do it for 1. Okay, so now that we know what our eigenvalues are, A0, A1, A2, we solve this for each one of those eigenvalues. So for the first one, which was A1 is equal to 0, what we have is that. So what we'll have is y is equal to 0 and x plus z is equal to 0 implies x is equal to minus z. So what we want to do ultimately is normalize these. But what we can do to start off with is let's just choose x is equal to 1, which implies x is equal to 1, y is equal to 0, z is equal to minus 1. Now you could say, well, why not do it the other way around? Why not choose x is equal to minus 1? But remember, if an eigenvector is a solution, then any multiple of that eigenvector is a solution, including a multiple of minus 1. So we're free in that sense to choose whether we take this as 1 or minus 1. As long as we're consistent for all the elements, it's still a solution. But if we define our A1 ket as 1, 0, minus 1, y is equal to 0, x is equal to 1, z is equal to minus x. But that's not normalized. How do we normalize it? Well, we get our inner product again. What's that going to be? Well, 1 by 1, 0 by 0, minus 1 by minus 1 is equal to 2. To normalize, we now need to multiply our elements by 1 over root 2. Similar process for A2 and A3. So A1, A2, A3 are that. Right, next part of the question. Which was, where's it gone? Yeah. Denote the eigenvectors of A by A1, A2 and A3. So, what we have now is a basis set. Set of basis vectors. And show that the set forms an orthonormal and complete basis. So remember, you need to show that it says AJ, AK. Let's just to use different indices for chains. Don't get confused between the K here and spatial frequency. It's got nothing to do with spatial frequency. It's just an index. It's just a number. It's just a label. So you've already done that for A1, the inner product of A1 and A1 in terms of when we were working out the normalization. So you've done that for A2, A2 and A3, A3. So you already know they're equal to 1. Just make sure that double check A1, A2 is 0 in terms of the inner product. A1, A3 is 0 in terms of the inner product. So in terms of that identity relation, which shows that we've got a complete basis, then what we have there is we're going to have, what did we call them? N. And we want to show that that's equal to the identity operator. So that involves, again, remember, and this is a really good example in terms of hammering home that message, that this is a scalar, this is a matrix. So let's do that. Ket bra for A1 looks like this. So basically what we're doing here is we're multiplying our column vector by our row vector, which gives us this matrix. Similarly, the ket bra, and we actually call it an outer product, for A2, A2. So we've got an inner product, which is, for example, this. And we've got an outer product, so bra ket. Think of it in terms of ket bra, which is that. Inner product, outer product. So let's do the outer product for A2. And what we get is that. And let's now do the outer product for A3. And what we get is that. Doing here is multiplying the ket, which is the column vector, by the bra, which is the row vector. And it's giving me a matrix each and every time. So we've got 3 matrices now. Now what we're going to do is we're going to sum them up. What we get is this, gratifyingly. So we get the identity matrix back. So we have a complete orthonormal basis on which we can build up any particular ket that we like. We're finished. That one.